about direct proof, indirect proof, which are the contrapositive and the contradiction, and the PMI or the mathematical induction. When we say direct proof, it is a procedure for proving the truth of P implies Q. First, we must assume that our hypothesis, which is the P, is true. Then we build an argument using the chain of implications directly leads to a conclusion, which is the Q, that it is a true statement. We have here our statement, the product of two odd integers is odd. We are going to prove this statement if it is true or not by using a direct proof. We assume that the product of two odd integers is odd. Assume that the product of two odd integers is odd. Let x be equal to 2m plus 1. We added 1 to make it an odd integer. Y is equal to 2n plus 1. For some integers of m and for some integers of n. To show that x times y is equal to 2m plus 1 times 2n plus 1. 2m times 2n is equal to 4nn plus 1 times 2n is equal to 2n plus 2n times 1 is equal to 2n plus 1 times 2n is equal to 2n, and then plus 1 times 1 is equal to 1. Next step, we will going to get the common factor, which is 2. And then it will become 2m n plus n plus n then plus 1. The 2mn plus m plus n are all integers, so the answer will going to be an integer. So we will going to use the variable a to represent the integer. Then copy the 2 times a plus 1. So we come up with this answer, and it is an odd integer. Thus, the product of two odd integers is odd. We conclude that the product of two odd integers is odd. So the statement is true. The next theorem that we will going to tackle about is indirect proof, which are the contrapositive and the contradiction. When we say contrapositive, we begin assuming that RQ is false, then we proceed to show that RP is also false. That is, we prove that the negation of Q implies the negation of P. Then we conclude that P implies Q is true. So we have here the same problem, the product of two odd integers is odd. We are going to use the contrapositive proof to prove this statement. So we assume that the product of two even integers is even. Let x be equal to 2m and y be equal to 2n. To show that x times y is equal to 2m times 2n. So 2m times 2n is equal to 4mn. The next step, we will going to get the common factor, which is 2mn. Since 2 times 2mn is equal to 4mn, and the 2mn inside the parenthesis is an integer. So we will going to use the variable a to represent the integer. We will copy the 2n times a. Thus, the product of two even integers is also even. We conclude that the product of two integers is also even. When we say contradiction, we begin assuming that P implies Q is false. Then we build an argument that leads to a contradiction. We have the same problem. The product of two odd integers is odd, and we were going to use the contradiction proof. We assume that the product of two odd integers is even. So from this statement, we can see that the product of two odd integers is even. So let x be equal to 2m plus 1. Since we added 1 after the 2m to make it an odd integer. So y is equal to 2n plus 1. For some integers of m. For some integers of n. To show that x times y be equal to 2m plus 1 times 2n plus 1. 2 times 2n is equal to 4mn plus 2m times 1 is equal to 2m plus 1 times 2n is equal to 2n plus 1 times 1 is equal to 1. Next, we will going to get the common factor, which is 2. So 2 times will become 2mn plus m plus n and then plus 1. Since 2 times 2mn is equal to 4mn and 2 times m is equal to 2m, and then 2 times n is equal to 2n. So the 2mn plus m plus n are all integers. So the sum of these integers will be an integer. So we're going to use the variable a to represent the integer. Copy the 2 and times a plus 1. Thus, the product of two odd integers is odd. So it contradicts the statement, which is the product of two odd integers is even, and then we come up with this answer that it is an odd. So the statement is false. Now we will going to prove a statement by using PMI, or principle of mathematical induction. We have here our statement, our given statement 1 over 1.2 plus 1 over 2.3 plus 1 over 3.4 plus 1 over 4.5, that plus 1 over n times n plus 1 is equal to n over n plus 1. We need to prove this formula that it is correct for all natural numbers. That's what n is greater than or equal to 1. So let's look at our solution. Let the given statement be P of n. So we have here our statement. P of n is equal to P of n 1 over 1.2 plus 1 over 2.3 plus 1 over 3.4 plus 1 over 4.5, that plus 1 over n plus 1 is equal to n over n plus 1. Our step 1 for n is equal to 1. We need to find the nth term of the left hand side and the right hand side. So we have our n is equal to 1. So we are just going to replace n into 1. So we have here 1 over 1 times 1 plus 1 is equal to 1 over 1 plus 1. 1 plus 1 is equal to 2 times 1 is equal to 2. So we came up with the value of left hand side, which is 1 over 2 is equivalent to the right hand side, which is 1 half. So our P of n is true for n is equal to 1. Our statement is true for the first natural number. So step 2, assume that the statement is true for some natural number of k. We have here our statement. We are just replacing the n into k. So 1 over k times k plus 1 is equal to k over k plus 1. That 1. We are using the number 1 in the end because we're going to use this 1 in our step 3. Step 3. Now we need to prove that P of n is true for n is equal to k plus n. We are just replacing the k into k plus 1. So we have k plus 1, and k plus 1 so is equal to k plus 1 plus 1. And then k plus 1 over k plus 1 plus 1. K was replaced by k plus 1 over k plus 1 and plus 1. So we have 1 over 1.2 plus 1 over 2.3 plus 1 over 3.4 plus 1 over 4.5 dot plus 1 over k times k plus 1, since we are simplifying this term. That's why we get this from this. And this is the short term. So we can observe that this whole statement is the same as this statement. This statement. So we can now substitute the k over k plus 1 from this statement. So we have k over k plus 1 plus 1 over k plus 1 plus 2. Since we copied this term, then next step we will going to get the common term for each term, which is the 1 over k plus 1. And then the remaining term will be k over 1 plus 1 over k plus 2, since we already get the common term, which is the k plus 1. So 1 over k plus 1 times k plus 2 plus 1, since we multiplied the k to the k plus 1 in the denominator, and then we added 1 over k plus 2, since k plus 2 times 1 is equal to k plus 2. Next, 1 over k plus 1 times k squared plus 2k plus 1 over k plus 2. We get this term by using this formula. So next, we have 1 over k plus 1 times k plus 1 quantity squared over k plus 2. We simplify this term into this by using this formula. And then 1 over k plus 1 times k plus 1 times k plus 1, since k times k is equal to k plus 1 times k plus 1 over k plus 2. We get this 2 term by using this formula. So we cancel out the k plus 1 and k plus 1, since they are both the same. So our final answer would be k plus 1 over k plus 2. Hence, the p of k plus 1 is true whenever p of k is true. By PMI, or the principal mathematical induction, the statement is true for all natural numbers.